Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are studying approximate methods that work in the non-perturbative regime of the coupling constants. And what we have seen is that interesting physics, particularly phase transitions, etc., occur when the coupling constants are not small or not large. So there are no small parameters that we can use to find the answers reliably. And so we need to look for approximate methods, and the sort of approximate methods that we are looking for aim to see whether, given a model, we can quickly find the phase diagram without too much of difficulty to ensure that at least the starting point of our model has the essential physics that we are hunting for. So our methods may not describe the details of the phase transitions, etc., but hopefully it will tell us at least what are the distinct phases and so on. So in this direction, we have explored a method called as the Feynman variational principle. So the idea of the Feynman variational principle is to come up with a proxy Hamiltonian, some other Hamiltonian that you believe describes the similar physics as what you are trying to model with your actual system, and you try to have some set of parameters in that Hamiltonian, and you try to optimize those parameters so that you can give an upper bound to the free energy, and hopefully you can get some reliable results. But what we found was that when we studied the classical Ising model in arbitrary dimensions, we did it for arbitrary dimensions, we found that the system orders for any dimension, which is not quite correct given that we have solved the one-dimensional Ising model exactly. So what we sort of came away with was that one has to get a handle on this what is happening in low dimensions. Particularly, this approximation method seems to work in higher dimensions, work better in higher dimensions. Okay. So there is a problem with Feynman variational principle in the sense that one has to come up with some Hamiltonian that one believes describes the physics and so on, right? So that requires some experience of certainly, and you have to also look for more exotic Hamiltonians, etc., if you need to model something complicated. So in this lecture, what we are going to do is, we are going to look at another way of approaching the problem called as mean field theory. Okay, so this I'm hoping will be a very useful tool for you, not only in this course, but hopefully if you get into research, you will find that many problems, the first shot you will take at any given problem is by mean field theory. Okay, so let me give you an idea of what mean field theory is, and then we can get into the details and try to see how it is formulated formally. So what happens in mean field theory is that in most cases that we study, your Hamiltonian will be written as a sum of terms. Typically there will be some local interactions, like for example in the Ising model it's interactions on links and so on. So this is very typical, most systems have such local interactions. Now when you have these local interactions, you will find that there will be products of terms that produce interactions. For example, there's spin at site I multiplying spin at site j. So that's the interaction between the spins. So the way we visualize this now is that each of these terms that are getting multiplied, they are some fluctuating objects. So this is the statement that I'm making here, that in many cases the Hamiltonians can be thought of as sum of products of fluctuating quantities. The general idea of mean field theory is to say that if I want to look at one fluctuating quantity and how it is quote unquote interacting with another fluctuating quantity, you might on the first round replace the fluctuating quantity that the first quantity is seeing by some mean value of that quantity. So in other words, that fluctuating quantity with which the quantity of your interest is interacting with gives a mean field or some mean potential or something like that on this quantity. And so we will try to see how this idea can be formalized. So once we are done with this, you will realize that we will end up with what are called as self-consistency equations. And the main strength, I must say, of mean field theory is that you can go into the non-perturbative regimes of your coupling constant and solve these self-consistent equations without recourse to perturbation theory in the coupling constants. The flip side is many times you may not be able to do this analytically, so you may have to use the computer, but that's not such a such a step back. So there is a great advantage in mean field theory over the Feynman variational principle in practical terms. The practical advantage of mean field theory is that mean field theory is built on physical understanding of the system. What I mean by that is, I mentioned about terms in the Hamiltonian. So you can know what each term, what physics they contribute. For example, do they promote ferromagnetism, or do they promote antiferromagnetism? So you can, or they promote disordering, whatnot. So you can look at the term in the Hamiltonian and you can ascribe its motives, if you wish, and then try to placate the motives by choosing the correct mean fields, etc. So in the sense that this is a very physics oriented method, so you don't have to make mathematical guesses. You can look at the Hamiltonian and you can try to get its mean field by appealing to the physics of the problem that you are trying to study. And in particular, if you have experimental input, then you can certainly use that to construct mean field theory and so on. So this is the background of mean field theory. So let me go through the formulation of mean field theory. So we'll start with a system defined by some set of configurations. So we'll call this the set C, and we have a Hamiltonian, which, as I advertised, we are now formally writing this. We will see examples of this, very clear and specific examples of this maybe in the next lecture, but for now we will just assume that the Hamiltonian is a sum of terms which are products of two observables or operators or some functions of the configuration. So if you take the Ising model, for example, this alpha will be the links and A will be Si and B will be Sj, the two sites that are on the links. So such a structure generically emerges, right? And I have not written the coupling constants of this Hamiltonian explicitly, so you can absorb that into definitions of one of the A or B or whatever. So for this discussion of mean field theory, we don't need to show the coupling constants explicitly. When we work out the examples, we will put the coupling constants in the right place. Okay, so this is what we are starting with, and we can compute the partition function formally. We can write it down. Of course, we can't compute it, otherwise we won't be doing approximations. And the probability distribution over the configuration space, namely the probability of realizing configuration C, is given by this ratio, which is the Boltzmann weight by the partition function, the Gibbs distribution. Okay. Now, the way we are going to start thinking about this problem is that we are going to think of each of this A and B as fluctuating quantities. They are thermally fluctuating quantities. So each of these quantities have a mean value, right? So they have an average value on our Gibbs ensemble, and that is this expression, well known elementary expression. And the same thing, B also has an average value. So now to proceed with the discussion, I am going to do a set of manipulations. It may seem a little mathematical jugglery, but just hold on. At the end of this discussion, you will see that it will lead to a nice physically appealing result. So I can define some quantity which is called as the fluctuation operator or the fluctuation observable, which is in any configuration you take the value of this A in that configuration and subtract from it this mean value. So if you now take the expectation value of this quantity, it will turn out to be 0. Of course, mean value of fluctuation will be 0. And the same thing for this B. Okay. Now what I am going to do is I am going to view my field A, this A, as a sum of the mean value plus the fluctuation. So I am now visualizing A as if it is something that has a mean value and it has a fluctuation about the mean value. So note that this mean value does not depend on the configuration, it is just a mean value. Okay, and same thing for B. So the terminology people use in the physics field is that we call this the mean field, right, and plus the fluctuation delta I. So A alpha should be thought of as the mean field plus the fluctuation. Now what I am going to do is I am going to explore this term. I am going to take A alpha, B alpha, and I am going to take a product of these two. And I am going to explore what this quantity is. So all I am doing is I introduce this idea of writing a field as a mean field plus fluctuation. I am simply using that definition into the left hand side. I am injecting that in that, and I will get this result. Now if I multiply through this, I will get 4 terms. So one is the product of the mean fields, the other is the mean field quote unquote talking to the fluctuation of B, mean field of A talking to the fluctuation of B, and the mean field of B talking to the fluctuation of A, and then if you like the correlations between the fluctuations. If you take the expectation value, this will be the correlation between the between the fluctuations. So it's a product of the fluctuation terms. Now what we are going to say as an approximation is we are going to set this term to be 0. So we actually set this term to be 0. This is the approximation. Okay. So what it does is it drops the correlations between the fluctuations of A and B. This is the central approximation here. Okay. So what does this gain us? All right. So now what I am going to do, I am going to take this term, which is exactly what we had here, and I am going to write this as approximately equal to this term where I have dropped the correlations of the product of fluctuation terms. So I have this term here, and you see, so this is mean field of A multiplying the fluctuation of B. Now what I do is I put back the definition of the fluctuation. So what I do is I take this and write delta B alpha of C as B alpha of C minus mean field of B alpha, and same thing I do here. So now you will see I will get A talking to the mean field of B, B talking to the mean field of A, I will get plus A alpha product of mean fields, and I will get 2 times the product of mean field from the other 2 terms, and that will cancel, or that will change the sign of this because minus 2 plus 1 is minus 1, right, and you will get this term. So what is it that we have done? By rewriting this, by going through this sort of somewhat algebraic way of doing things and making the approximation of throwing away the product of the fluctuations, we landed up with the following result, that the product of A and B, which are 2 fluctuating quantities, can be viewed as A alpha of C, which is a fluctuating quantity, feeling or seeing only the mean field of B, and this quantity is the fluctuating B quantity seeing the mean field of A, minus A alpha, B alpha, mean fields of A alpha and B alpha. So you may wonder, how do you understand this? So what you can do is, suppose you were to take expectation values on both sides. So now you will see that you will get expectation value of A, expectation value of B, and so on, and then you will see that if you didn't have this term, you would have got 2 times expectation value of A and expectation value of B, which is not nice, right? So this one keeps track of that bookkeeping, if you wish, and you will get that in this world, expectation value of A, B will be expectation value of A, expectation value of B, which is exactly throwing away these correlations between A and B. Okay. So this is the interpretation of this approximation we are making. We are saying that each fluctuating object sees only the mean field of the object with which it is interacting. Now you might wonder whether this is too drastic an approximation. Well, it could be. It could be if the fluctuations are, quote unquote, if these fluctuations and correlations between the fluctuations are strong. Okay. All right. So this is the approximation. All right. So now let's try to push this into a calculation. Let's try to see whether we can make a scheme for calculating phase diagrams and all if we start with this. Okay. So what I'm doing is I'm starting with the Hamiltonian. This is the exact result, and I replace this term by the mean field term here, right? So if I do that, I will get a mean field Hamiltonian, which is this quantity, right? This is the mean field Hamiltonian. I am replacing my original Hamiltonian by this approximation. Now the hope is, of course, that I will be able to solve this, but this problem is, this approximation is already running into a problem, right? The idea is, suppose I have this mean field Hamiltonian, I could solve this partition function, I could get the probability distribution, I can find the mean field free energy, and I could do this. So I could go through this full cycle of calculations. The only problem here is I do not know the values of these quantities, because finding the values of those quantities is same as trying to find the partition function, solving the original partition function and summing over the distribution function over the probability distribution over the space of configurations and evaluating these expectation values. So yes, I have set up a mean field Hamiltonian, but it does not, it has quantities which I do not know the value of. So what is the strategy we have to adopt to try to address this problem, right? So this is the issue. The issue is that H mean field depends on these unknown quantities, and we have to come up with a way to handle this. So here is where mean field theory will make its second approximation. So remember, these expectation values were computed in the ensemble of the original Hamiltonian without making any assumptions about fluctuations and without throwing away any correlations between fluctuations or any such thing. So what we are now going to say is that this mean field Hamiltonian, whatever we are going to get out of that mean field Hamiltonian, those will be the expectation value of A that we will use. So wherever we see expectation value of A, you will see, you will replace it by whatever you get from the mean field Hamiltonian. Okay. So this is the replacement that we are making, and what you will end up getting is that the mean field Hamiltonian is now, instead of the expectation value on our original ensemble, we will have the expectation value on mean field. But you may wonder, but I have not solved this Hamiltonian yet. So how can I find the expectation value on this? So if that question came to your mind, yes, that is indeed the correct question. These are still unknown. So what do we do? So this is where the self-consistency conditions come in. So, the statement is that suppose I knew these values and I compute the Gibbs weight or out of this Hamiltonian and compute the expectation value of A's, then I should find that that is exactly same as what I put in, self consistent. So, you make an ansatz to say that, oh, the mean field is this, but you have to ensure that the ansatz is correct and the value of mean field expectation value that you get from the ensemble is same as what you put in. So, that will give you, now you can see if there are, like, let us say that there are 20 alphas in your system, there are 20 different terms in your system. So, you will get 40 different equations. For each alpha you will get one term, one equation for the A alpha and one equation for B alpha. And this will tell you that if I solve these equations, I will find the correct values of A alpha mean field and B alpha mean field in such a way that this equation is self consistently satisfied. That is the solution, and the most important thing we have to ensure is that these equations are highly nonlinear and you have to solve them non-perturbatively in whatever coupling constants are hiding in this notation. So, I have not explicitly shown the coupling constants here, but there could be many coupling constants hiding in this notation, and so you have to ensure that the solution, finding the solution of these highly nonlinear equations is performed in a non-perturbative fashion, and performing it in non-perturbative fashion will give you access to regimes of coupling constants where interesting physics is likely to take place. For example, you could have a phase transition, you could go to a new phase and so on. So, this is the idea of mean field theory. Okay. So, let us discuss what are some of the features of mean field theory. So, what you will find is mean field theory is actually easy to use in the sense that many Hamiltonians that you deal with in working physics offer themselves for mean field decomposition. So, if you take any particular model, say for example, you take the model of attractive fermions, then it offers a natural way of finding the superconducting ground state using mean field theory, and so on. So, it's very physically appealing. Like I mentioned, physical motivation gets into making meaningful mean field decompositions. And what happens in many cases is that these mean fields, like the expectation value of A alpha and those kind of quantities that we encountered in the last slide, they will turn out to be the order parameters themselves, right. So, if you find that in a regime of parameters, those order parameters are turning out to have non-zero value in the self-consistent solution, then you can conclude that you have broken symmetry or you have a phase characterized by that order parameter. Okay, it offers even further and very interesting possibilities. I am talking about mean field theory here. What you can do is, if you take a term, you will find that in many cases you can break it up. So, what you call as A alpha and B alpha, that's the term that you are writing down. It can be arranged into A alphas and B alphas in different ways. So, you can break it up in different, the language people use is channels, right. And what this will give you is, you can address questions like competing orders. So, for example, something wants to become an antiferromagnet versus it wants to become a superconductor. So, you can try to settle this issue by giving some weight on each of these channels and figuring out what is the optimal weight and so on, right. And it is of particular interest in particularly interesting because it can address experimentally interesting systems. So, the biggest challenge in mean field theory typically is not setting up the mean field equations. They are typically straightforward because you can in most cases set it up very straightforwardly. The solution of the mean field equations can be sometimes challenging, and typically if you want really non-perturbative answers, you have to use a computer. And the difficulty here is that the equations are highly nonlinear. You can see that there is a linear term on the left side, this exponentiated and so on. So it involves transcendental functions, and variety of such mathematical difficulties can come up. Nevertheless, it's a very, very popular method. And finally, you might wonder, how is this connected to the Feynman variational principle that we have seen? So you can view mean field theory as a type of Feynman variational principle as well. So another way of thinking about it is that you remember that we had defined these mean fields associated with the objects A and B. Those mean fields, the expectation value, you can think of them as lambda parameters. In fact, if you can write down an energy function based or some free energy function based on these mean fields, then this mean field theory will be a way of implementing the Feynman variational principle. In any case, Feynman variational principle can be more general. You can come up with variety of Hamiltonians. In mean field theory, you look at a particular problem and you try to find what is a suitable way of decomposing the terms to address something concrete physics, some concrete physics of the problem. Okay, so let me summarize this formulation lecture of mean field theory. So we viewed the Hamiltonian as a sum of products of fluctuating terms. We replace these products with one object seeing the mean field of the other object and vice versa. And we noted that what this does is it involves ignoring the correlations between the fluctuations of these quantities. So finally, these mean fields that we had, they were not given to us, so we had to find a way to find them. So what we realized was that we can come up with a scheme in which we assume we don't know them, we put in some values, and we want to ensure that the output of the ensemble in which you have put the values are same as the values that you put in. So that will give you a set of equations to work with, by which you can solve for those mean field values, and the solution of the mean field values will give you a simpler problem, the mean field problem, and from which you can extract some physics out. Okay. So as I mentioned, mean field theory is definitely a tool of choice for practicing physics people. So many, if you see an experiment that you want to understand, typically the first thing you will do is, after you write down a model for what you want to explain, you will do some simple mean field theory to make sure that you are in the right ballpark and you have got some correct things going, and you can match some part of the experiments at least. Okay. So this is what we have done in this lecture. We have formulated mean field theory, and in the next lecture, I am sure you will enjoy mean field theory in action. We will solve the d-dimensional cubic lattice Ising model using mean field theory, and I am sure you will have a great time learning about that. So please join me for the next lecture. Thank you.